Okay, so now what we are going to do, so now we are starting with the block level design approach. So in the block level design approach, we can design more complex circuit using the block level design method. Okay, so we can design more complex method, more complex circuit using the block level design method. And what's the block level design method? So in the block level design method, what we do, it relies on the algorithm or formula of the circuit, which are obtained by decomposing the main problem to sub-problem recursively until small enough to be directly solved by the block of circuits. And we already covered in our last lecture. So basically, when we want to design a big block, let's assume we want to design a big circuit like a 16-bit adder. So this 16-bit adder can be designed using small blocks of 1-bit full adders. Okay, so this was how we did it in last lecture. Okay, and then we also did one example of BCD to HSP code conversion. It was already done. Then the 16-bit adder, 16-bit adder can be designed using 16 1-bit full adder, or 16-bit adder can be designed using 8 2-bit adder, or 16-bit adder can be designed using 4 4-bit adders, or 16-bit adder can be designed using 2 8-bit adders. Now in today's lecture, so we will design an adder cum subtractor. So before designing an adder cum subtractor, so I will explain that how we can design a subtractor using the block level design method and how we'll do it. So in hierarchical design approach, what we do, we decompose a complex circuit into smaller pieces called blocks, and then we decompose each blocks into many smaller subblocks, and we repeat until the blocks are small enough. It is based on the algorithmic principle. So algorithmic principle says that if we have a complex circuit, we divide that complex circuit into many small circuits, and then we connect all of these small circuits together to build the whole thing. So that was the thing. So let's say we want to design a 16-bit adder. So we connect all of these 16 1-bit full adder in a particular phase, in some particular fashion to design the big block. Okay. So now what this is our objective. So what, let's assume if we want to design a subtractor. How can we design a subtractor? Okay, can you see here? This is the block level diagram of subtractor. Can you see here the block diagram of subtractor? Okay, now we want to perform this operation. So we want to perform this operation. What is the operation? Do you see the operation? Yes. What is this operation? It is a subtraction or adder? Yes, please help me. It is a subtraction or adding? Are we adding or are we subtracting? I'm not hearing your. I'm not hearing.
Subtracting.
Yes, it is a subtractor. Okay, what we are subtracting. So now what we are doing? So we are doing a subtraction. We are subtracting B from A. Okay, what is the color for A? What is the color of A in this example? What is the color of A here? Yes.
Red.
Right, the color of A is red. So now can you see here? Now we have the color of A, which is red here. Okay. So now the color of A is red. Oh, what? No, there's a problem. 1 minute. I need to just make the display setting and identify duplicate this. Okay. Okay. So what is the color of A? Help me. Yes. And it is a what is the size of A? Help me. How many bits are there? A is a 4-bit signal.
4
A is a
bits.
4-bit signal. So this is a 4-bit signal. Then we have B, which is the black color, which is the black color, and this is a 4-bit signal. And now we want to compute C. So compute C. C is also a 4-bit signal. So this is 4 bits of C, which is actually C3, C2, C1, and C0, and then A. Okay, now if you want to compute this, C is equal to A minus B. So what we do, so now what you see, so now I'm going to do this. So now what we want to compute C, so C is equal to A minus B. Okay, now how can we compute A minus B? So how can we compute A minus B? Using 2's complement method. Yes, using 2's complement method. Yes. Yes, what is the 2's complement method? You did it in your number system. Help me. How can we compute C?
Adding a negative number, like
Now adding a negative number. So now how can you see? Okay. Now we have A. Please remember now in this example A is an n-bit number, 4-bit number. So can you see? Can we write it here? So what is A? So we can say the binary of A. 2 means the binary of A. And then we say plus. What should we write? Now I'm now using the black color. So what is minus B equal to? So now this minus B is equal to the 2's complement of B. Got it or not got it? Okay. So what is minus b? So minus b is actually, so minus b, and we already know number system. So minus b is actually the 2's complement of b. Okay. Now when we see, okay, how can we compute 2's complement? Yes. Can anyone help me?
Invert all the bits and add 1.
Yes. So we say we invert all the bits and then we add one. So now can you see here? This is actually the a 2's complement plus, and then we can see now we have say, so now what we write. So we can say it is actually the 2's complement can be computed by adding ones to the ones. I mean, any question? Should I got it? And then how we compute this ones complement? How can we compute this ones complement? So this two's complement is equal to equally one's complement of b plus one. And let's assume this b is actually b3, b2, b1, and b0. So now what is b? B is actually what? b3, b2, b1, and b0. Okay, this is the binary of b. Now if you want to compute one's complement of b, so one complement of B will be actually B3 bar, B2 bar, B1 bar, and B0 bar. Any question? So now how can we compute then? C. So now my C is equal to, which is actually now this the binary of A, and then plus. So basically, no, sorry, this is just I can say. So can I write something like this one? I can write it here. Yeah, let's assume A is a 4-bit. So this is actually A3, A2, A1, and A0, which is the binary of A, and plus. And now the 2's complement of B. So what is the 2's complement of B? It is actually B3 bar, B2 bar, B1 bar, and B0 bar, and then just one. Okay, now so now if you do that, so now this is now we have done it. So now what we are going to do, so now I'm copying this and pasting it. As you do it in your homework, you are copying and pasting. So control C, control C, control C, and then I paste it here in the next slide. So paste image, now C. Okay. Now we want to design. So, okay, this actually C. Please remember, this C is nothing but this C is nothing but this C is nothing but C is equal to A minus B. So this C is nothing but, so control C, this C is nothing but this C is equal to A minus B. Okay. Now remember we have remember if you remember we have a 4-bit adder. What was the 4-bit adder? So 4-bit adder look like this. So this is a 4-bit adder. And 4-bit adder has three inputs: x3, x2, x1, and x0. Okay, and then y3, y2, y1, and y0. So this is a 4-bit adder, and then we have a C in, and then we have C out. So how can we design? So now this is our objective. So how can we design? So our objective, how can we design? How can we design a 4-bit subtractor using a 4-bit adder? Got it? Okay. Now, where should I connect A? Can anyone tell me where should I connect A? Anyone? And then we have, S3, S2, S1, and S0. Where should I connect A? Anyone help me?
X,
X. So what should be the value of X0, X1, X2, and X3? Help me. I can connect
A0,
A here.
A1, A2,
A1,
A3,
A2, and A3. And where should I connect B? Yes.
Y,
No, B or B bar?
B bar,
B2 bar, B1 bar, B2 bar, and then B3 bar. And please remember, this is the ones complement. So this is actually, can you see here? This is now the ones complement, not the twos complement. So this thingy is the ones complement. So this is b3 bar, b2 bar. So this is actually now the ones complement of b. So this is actually b's ones complement. But now we have an additional one here. Can you see the one here? This one. What should we do with this one? Can anyone help me? Yes.
Put it in C in.
Yeah, so we put this in C in. So we put this thingy in C in. So what we do? So now we put this in C in. So this we see. So C in is now one. Okay. What now? This now we have the output C. C is now a 4 bit. So where should C0 go? Can you help me? C0 is here. C1 is here. C2 is here, and C3 is here. So in this way, we have designed. So now in this thing, we have designed a subtractor using a 4-bit adder. Any question? Okay. Now another question. So now can you see here? If we go to the next
Professor,
slide.
I have a doubt.
Yes, please go ahead.
Would the C out if A3 and B3, or sorry, X3 and Y3, if they were both one, would the C out be the overflow?
For the overflow, okay. Now, if there is an overflow, I will explain the circuit of the overflow later on. Can we hold on for like 30 minutes or 40 minutes?
Okay, Professor.
Okay, so at this point of time, I'm not going to explain overflow because I will explain overflow later on. But this will be at the end of the lecture. Okay. Okay. Now I'll
Okay.
explain it. This is a slide on that. Okay. Now let's assume if we want to. So, another question. How can we design? Now this may be another task. Maybe this is a task for your midterm. So please be attentive. Not for this midterm, but for the next midterm. How can we design? How can we design a 4-bit subtractor using, this is my task. This may be, how can we design a 4-bit subtractor using full adders? Now, if you're designing a 4-bit subtractor using full adders, so now what we have now? We have this thing. This is the first full adder, the second full adder, the third full adder, and the fourth full adder. Okay, if you remember in the full adder, we have actually A, B, and C in and C out and S. Then we have A, B, C in and C out and then S. Then we have A, B, C in and C out and S. And then we have A, B, then we have C in, then we have C out, and then we have S. Got it? So this is that it. And now can you see here? Now if you want to design this thing here, okay, so now if you go here, so now we need to compute this thing. So we need to compute this thing. So now we have this thing, Control C, and now we put it here. Now we have this thing. So we want to compute this. So now please remember this is now C in. So now this is now C in. So this is now my C in. This scene will go here. This scene will go here. One. Now we have A. What should go to A? Help me. Here. What should go here?
A0.
A0 should go here, A1 should go here, then A2 should go here, and then A3 should go here. Now what about B?
B naught, B0 naught, B1 naught.
Bar. And this is B1 bar. This is B2. Because now we
No.
are using the same different color. So basically for B it's black color. So then can you see here? This is actually, so now this is a black color. So it's a black color. So what I do? I change the color. Okay, so now this will be actually B0 bar, then this will be B1 bar, this will be B2 bar, then this will be B3 bar. Any question? Clear? And since this is the bar, so we need an inverter here. So we need an inverter for B0, and then we need an inverter for B1, then we need an inverter for B2, and then we need an inverter for B3. Any question? We need 4 inverter. And now the C out for this will go to the carry in for this stage, and C out will go, and this will go, and this is my C4 now, which is actually C, final C out. And this S, now we have, then if we go for this, so now we have what? Let me, S0 here, sorry, not S0, because we want to compute C, yeah? What should go here? C0 and C1 and C2 and C3. Any question? Any question?
No, Professor.
Should we proceed? Got it? Any question? Okay. Now what we are going to do now? So basically this is all the work that we did. So now this is the work. So now this is all this was for the other class. So we did this, and then okay. Now what we are going to do now? So Control C. So now what I'm going to do? Okay. Okay. Let's assume now that this is or another objective. Let's assume we want to compute something. Okay. Let's assume we want to compute P is equal to K minus J. And let's assume all of these signals. Assume that all of these signals, all of them are 8-bit data. It is 8-bit data. So if it is an 8-bit data, so now this P is nothing but is what is this P? P is actually P7, P6, P5, P4, P3, P2, P1, and P0. And we want to design this using an 8-bit adder. So we want to design this using an 8-bit adder. So now if you look at an 8-bit adder, how an 8-bit adder will look like. So an 8-bit adder will like look. So we have the signal X7, X6, X5, X4, X3, X2, X1, and X0. Then we have Y7, Y6, Y5, Y4, Y3, Y2, Y1, and Y0. Then we have C in, and then we have C out, and then we have S0, S1, S2, S3, S4, S5, S6, and S7. Any question? So S6 and S7. Now, if you want to design this thing, okay, K minus J, what should we do? Help me. What should you do? What should go to X0, X1, X2, X3,
P0,
X4?
P1.
Hmm?
Sorry, K.
K0, K1, K2, K3, K4, K5, K6, and K7. Any question? Clear? And what should go to Y0?
J0.
0 bar. Because this is a subtraction. J1 bar, then J2 bar, then J3 bar, then J4 bar, then J5 bar, then J6 bar, and then J7 bars. How many inverters do we need? How many inverters?
8.
We need 8 inverters. And what will be C in now? Help me. C in
1.
1. And what about S0? What should I connect to S0? Help me.
P0.
P0, P1, P2, P3, P4, P5, P6, and P7. Any question? Should we proceed now?
Professor,
Yes.
is this the two's complement or only we're subtracting?
We are subtracting because you know what is P minus J. So now if you go to this P, now okay, I will explain it. So now in the next slide. Okay. Now can you see? Now if you want to have P is equal to K minus J, so we can write this as P is equal to K, which is actually 2's complement, plus which is J 2's complement. Got it? This is the binary. So this is actually K of 2 plus J of 1's complement plus 1. Got it or not got it? So a subtraction. So after a subtraction, a binary subtraction. So now what I will write. So a binary subtraction is nothing is actually an addition operation. And how can we do the subtraction? So subtraction can be done by computing the 2's complement of the number and add it. I hope I answer your question. Yes.
Yes, okay.
Do you have any question now? Is it clear?
Yes, it's clear.
Okay. Now, okay. Now I'll ask you another question. So please help me. Like let's assume, and now please help me. Let's assume that we have t. We want to compute t. Okay, and t is equal to a minus b minus c plus d. How can we compute it? So we can compute t is equal to what? A, because a is now positive a. So we will compute a, the binary of a, then what? Plus what? But 2's complement, because it's negative. So 2's complement of b plus, help me,
C2's
then what? Help me.
complement of C.
2's complement of c, and then what? Binary of d or 2's complement of d?
binary.
Binary. You got it or not? Got it? I hope I answered your question.
Okay, I got it. Thank you.
So this is how you do the computations and so. So whenever when we have negative numbers, so okay. Now if you do that, even if you do that, so this is actually and this b is nothing but b1's complement plus 1, and this c2's complement is nothing but c1's complement plus 1. Got it? Any question?
Yes.
Good. Now what we are going to do now? Now what we are going to do? So now we did these things. So now what we are going to do? So now I can delete this thing, because this is this for the other one. So we did this. Now we implemented this one. We already did this. Okay, we also did this. Yes. Okay, now this is a tricky question. Now there is a tricky question. Okay, so what we are going to do now? So now what we are going to do? Now this is a tricky question. Now copy. Okay, so now question. Let's assume we want to design an adder cum subtractor. So let's assume we want to design an adder cum subtractor. So let's assume this is the block diagram of an adder cum subtractor. So this is the block diagram of an adder cum subtractor. We have two inputs. The first input is A. Okay, that's the black color. The first input is A. And the second input is B, which is actually, I will use a different color now. So the second input is B, which is now the green color. And let's assume my output is C, which is now the black, the red color. Okay, and now we have, okay, and now we have a select line. So now we also have select line. So we can call it a select line. So this is my select line S. This is called a select line. Okay, okay. Now we want to design. Assume that we want to design an n-bit adder cum subtractor. N-bit adder cum subtractor. N-bit adder subtractor. And let's just take an example. So let's take an example. So let's assume we have an 4-bit adder cum subtractor. So now if we have a 4-bit adder cum subtractor, so now this is my 4-bit. Now we want to design a 4-bit adder subtractor. So 4-bit adder cum subtractor. This is the block diagram. So now we have the first input A, which is actually what? A3, A2, A1, and A0. Now we have the second input B. What will it be? Help me. Yes, can you help me?
B0 bar.
No. Adder cum subtractor. No, I will explain this later on. We are going to design the internal of this circuit. It's not B2, B3, B2. Just the input is B3, B2, B1, and B0. And if we have bar, we can design it inside. Okay. Any question?
Okay,
And now
Professor.
we have select line S. So this is my select line S. And now what is my output? What will be my output? What should I write in output? Help me. Yes. Output C. C3, C2, C1, and C0. Now I go back to the previous slide. So now you can say, okay, now the output C now depends on the select line. So now we can say, so there are two possible values of select line. So select line has two values. Since it's a 1-bit signal, so it has two values. So what is the possible value of S? Help me. 0 and 1. Okay. If S is equal to 0, then we want to do an addition. So C will be now equal to, basically A plus B. Got it or not got it? And if S is equal to 1, C will be now. So now I'll use different colors because the colors are always put. So A plus B. And now if C is equal to S is equal to 1, we want to do a subtraction. You got it or not got it? So now the value C now depends on the select line. So we will do an addition if S select line is 0, and we will do a subtraction if select line is 1. Any question? Any question? Got it or not got it? Okay. Now what will be the, let's say if you want to do this is just like doing some kind of a C code. In C code we say, okay, if S is equal to 1, so C is equal to A plus B, and else what will you see? Help me. This is just like an equivalent for this thing. Any question? Yes. Now $1 million question. $1 million question. Now we want to design this adder cum subtractor. So now we want to design adder cum subtractor. Okay. Now we want to design adder cum subtraction. Yeah. Okay. Now if you look at here. Okay. Now if you look at here, now this is my C. We want to compute C. C is equal to A. Either C will be either A plus B or C will be equal to A minus B. Now in both cases, now can you see here in both cases? So in the first case, so now I'm looking at the first case. A is constant or not? Help me. Yes or no?
A and B are constants.
No, A is constant, but in second case it will be plus B or plus minus. Can we further elaborate this? So now what I'm going to do? So what I'm going to do now, I'm now going to further elaborate it. So can I say something like this? So let's assume if S is equal to 0, so C will be actually equal to, if S is equal to 0, we need to compute what? So we can we compute A plus B plus 0? Can I write like this? Any question?
Yes, we can.
Now I want to do it in addition thingy. So now can you see here? Now let's assume if it is A minus B, so this is actually A plus the binary of B and plus, so this is the binary of B. So this is actually A binary of B and this binary of B and then C. Now if A is equal to S is equal to 1, how can we write this? Anyone?
A in binary plus B in 2's
Plus what?
complement plus 1.
B into 2's complement.
Sorry, B in 1's complement plus 1.
Yes. B is 1 complement plus what?
1.
Clear or not clear? Okay. Now, can I write something like this? So now I'm going to further elaborate it. So now what I'm going to do, so now I'm going to control C, and then I'm control X, and then I can make it paste it here. There's an image. So now this is. So can I further elaborate this? So now there are two possible values of when S is equal to 1. Here in this case, when S is equal to 1. Can I further elaborate this? When S is equal to 0, so can I write something like, because it's a 4-bit thingy. So what can I write here? Can you tell me what should I write here? So can I write here S is equal to 0? So it is actually A3, A2, A1, A0 plus. Then what should I write? Tell me.
B3 plus B2 plus B1 plus B0 plus 0.
Any question? Any question? Okay. Now if S is equal to 1, how can I write this expression? Yes.
A is the same and all the B bits are inverted. And you
For
add 1.
B, we input all the bits because this it will be what? B3 bar, because this is 1's complement. B3 bar, then B2 bar, then B1 bar, and then B0 bar plus what? Help me.
1.
Any question? Okay. Now, if you look at here, this A. If you look at this A is same or different?
Same.
Same. Okay. Now, if you look at B, it is what? Same or different?
Different.
Different. And what about C in?
Different.
Different. But if you look at C in, so let's can I divide this into two different parts? And please think of an adder. Please think of a 4-bit adder. So now think of a 4-bit adder. So now how a 4-bit adder will look like. So now we have 4-bit adder. Remember, we have 4-bit adder. Remember. So the first input is what? X3, X2, X1, and X0. Got it or not got it? Then we have Y3, Y2, Y1, and Y0. And then we have C in, and then we have C out. Any question? And then we have S0, S1, S2, and S3. Remember? Okay. Now, can you see here? So in this case, we have two inputs. So now, so basically X3, X2, X1, and X0 is the same as A. Any question or no? Okay. And now what about Y? What should be Y? So now, can you see here? Now we have Y3, Y2, Y1, and Y0. So now we have Y3, Y2, Y1, and Y0. So Y3, Y1, Y2, Y0 should be same or different?
Different.
Okay. Now, if you look at C in, now this is another thing. C in. Now this is the same thing, which is C in. Now this is my C in. So C in. So can you see here? C in is the same thing as S. Am I right or not? C in will be 0 when
Yes.
S is equal to 0, and C in will be 1 when S is equal to 1. Any question? Should we proceed?
Yes.
Okay. Now this is can you see here? Now when we are solving this thing. So now what I'm going to do now? So what I'm going to do? I'm taking a screenshot of this, and then I will further explain it. Now, okay. Now what is the range? Let's say we have some index I. Now we have index I. So I call this as index I. Index I. What is the range of index I? 0 is smaller or equal to what? Help me. I is
3.
smaller or equal to 3. Because you know, now why am index I? Because this is an n bit, this is n bit. And now in this example, n is equal to 4. When n is equal to 4, the range of the index I will be from 0 is smaller or equal to I smaller or equal to 3. Okay, can we say, okay, now can we say, okay, now we have, can we say that yi, so now this is my yi, y0, y1. So can just like can you say it like this? So can you say y0 will be, please remember, y0 will be b0 if what, help me, if s is equal to 0,
S
s is equal
is
to what?
0.
And what will be y0?
B0 bar if S is 1.
b0 bar if s is equal to 1. Can we write it? Okay. In general, we can say yi will be equal to bi if s is equal to 0, and yi will be equal to bi bar if what?
S equal 1.
Okay. Now, so can you see here? Now y, now in this case, now what I'm going to do? So now we can say, okay, yi. So now we can say yi will be 0 if s is equal to 0, and yi will be equal to, sorry, it is equal to bi, and it will be equal to bi bar if s is equal to 1. Which gate has this property?
Not gate.
Which one? No.
The inverter.
Can you see now? Look at the block diagram now. It means that now yi depends on two signals. What are those signals? So yi now depends on bi and what? Help me.
S.
And s. So yi is now a function of bi and s. Help me. Am I right or not?
Yes.
Okay. Now, which gate has this property? If the input is 0, it will be the same input. Which gate has this property?
XOR?
Yes, very good, very good. It means that you are paying attention. That's very good. So now, why? Okay, now I'm going to do. Why I'm going to do? What I'm going to do? So basically, so now what I'm going to do? So I'm taking a copy. I'm going to Control C, and then I'm making it paste. I'm pasting it here. Okay, now I'm explaining this thing. I'm explaining this thing. So yi will be equal to bi. Okay. So now we have, if you do that, bi and s. So now we have bi and s. Okay, and now we have yi. So there are four combinations of bi: 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So yi, if s is equal to 0, now can you see here? Now if s is equal to 0, so now s is 0 here. What will be the value of yi? It will be the same thing as bi.
0 and 1.
And if it's 1, yes,
1 and 0.
it is 1 and 0. So can you see here? Now this gate, which gate has this property?
XOR.
XOR. So now we are using an XOR here. XOR gate has this property. And please remember, we also did it in using the laws of the Boolean algebra. In the Boolean algebra, we says, if we have yi, so now in this case, now we have what? Now my output is yi, and the first input is bi and s. If s is equal to 0, so yi is equal to bi exclusive or s. If s is equal to 0, so it means yi is equal to bi exclusive or 0, which is actually yi is equal to bi now. Any question? And now if s is equal to 1, if s is equal to 1, now yi is equal to bi exclusive or 1, and anything exclusive or with 1, if you invert it, so yi is equal to then bi bar. Any question? So now I have proved this thing using two methods. I have proved this using the truth table approach and also using the laws of the Boolean algebra. So this is the laws of Boolean. Any question? Any question? Now should we proceed? Is there any question? Please let me know. If no one is answering me, the exam will be difficult. There are 23 participants. The exam will be difficult because many students not here. No one is replying. Fiza, Junaid, Latifa. Okay.
No questions, sir. No questions. You can move on.
Okay, Junaid is at least here. Okay. Fiza is not here. Maybe I don't know. Okay. And then there is the student will say, "Oh, professor is boring. I'm sorry for that. I'm so boring." Okay. So now we want to design this adder cum subtractor. So can you see here? Okay, now we have this adder cum subtractor, this thingy. So now I'm now going this the whole thingy. So this whole thingy. Got it? So now we want to design this adder cum subtractor. So now what I'm going to do? So now I'm just maybe I will do this. Okay. So what I'm going to do now? This is now where is adder cum subtractor? Now we solve this 4-bit error, 4-bit error. So now this is okay. Now this is my error concept vector. Okay. Now we want to design this using the adder concept. Okay. Now we have a 4-bit adder now. What is now 4-bit adder? So now in a 4-bit adder we have x3, x2, x1, and x0. Then we have y3, y2, y1, and y0. And then we have c in, then we have c out, and then we have s0, this way s1, this way s2, and this way s3. Okay, a same for all. So what should I connect to as x0? What should I connect here? Help me.
A0,
A0, then
A1,
A1,
A2,
then
A3.
A2, and A3. Okay, now what about y? Please remember, now we prove it here. So now if you look at here, we prove it. What is yi? So what is yi? So yi is the same thing. So I'm copying it, and then you see here, paste it here. What is yi? Yi is bi and s. So basically, what is y0? So y0 will be what? Help me.
Is
BIX S.
It will be p0, and then what?
S
S. Now we have b1 here. Now there is actually b2 here, and then we have b3 here. What should be the second input to the exclusive OR gate? Help me.
S.
S, 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 and S. You got it or not got it? When S is equal to 1, it will be an inverter. When there is an inverter, it will compute to 1's complement. And what about C in? What will go to C in? Help me.
S
0.
S
S. Because when S is equal to 0, when S is equal to 0, so this will be B0 and it will do the addition. S is equal to 1, it will do the subtraction. Okay. What about, what will be S0 now? Help me. What should go here?
C0.
C0 C1 C2.
Any question? Okay. Okay. Now what are you? This is all how we design it. Now this is our design step. Now we want to analyze it. We want to analyze it. So now there are some slides. So now this is an adder cum subtractor. So now this is what I'm going to do. So this is the adder cum subtractor. Okay. Can you see this is the design that we designed? This is the same thing. Yeah. Yes or no?
Yes.
So this is my A. This is now my B, and this is my S. Okay. Now there are two possibilities. There are two for adder cum. When S is equal to 0, when S is equal to 0, so sin will also be 0 because S is 0, so sin is also 0 because we are connected to S is here. So this is actually what we do. We are adding. Okay, now when S is equal to 0, so y3 will pass here, y2 will pass here, y1 will pass here because it's not complemented. And then what will be my output? My output will be x plus y plus 0. And then when S is equal to 1, sin is 1, it will give me y3 bar, y2 bar, y1 bar, and y0 bar. It will be the 1's complement, and plus 1, it is actually the 2's complement. So it will give me the 1's complement of y plus 1, which is actually x minus 1. Any question? Or did I not got it? Clear?
Got it, Professor.
Clear or not?
Clear.
Yes.
Okay. Now I'm going to answer one of the questions which was raised by one of the students for the overflow. Remember? Who raised this question, please? Speak in mic.
Me, Professor Thomas.
Yes. You. What's your good name?
Thomas.
Thomas. Okay. Now can you see here? Okay. Now this was the OR gate. So now can you see it when we have y and s is equal to 0, f will be y, and if we have 1, it will be y bar. And we did this. So this is one complement of y. Okay. Now this is how we did this. So just like this. Okay. Now coming back to your number system thingy. Coming back to your number system thing. So now this is in a number system. Okay. Remember, this is the same slide that I taught you in the number system lecture. Remember or not?
Yes.
Now, if you look at this number system thing, we have something in red and something in green. What is in red and what is in green?
C in and C out.
No, please remember this is also C in, 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 but this is actually the C in from the last stage. So the red color shows me the C in from the last stage, and the green color shows me the C out. Got it or not got it?
Got it.
Okay. If they are same, what does it mean? Is there any overflow or no?
No overflow.
No overflow. So can you see here? So now can you see here there will be no overflow. Okay. Now if they are different, what does it mean?
Overflow.
Now what we are going to do? Now this is very important. And now I'm going to elaborate it. Now I'm going to now elaborate it. Okay. So what I'm going to do? I'm going to copy this and paste this as you do it in your homework. I know that everyone does this, and they will also do it in in the online exam. I know that. What should I do? Okay. Now can you see here? This is the first stage, the second stage, the third stage, the fourth stage. Okay. Can you see here? What is okay? Now we have different C in. Okay. So this is actually now. What is this thing? You help me. C0. What is this thing? Help me.
C1, C2, C3.
Two, and then what?
C3.
And what is this thing? Help me. This thing. Help me.
C4.
And C4 is actually C out here. Got it or not got it?
Got it.
Got it. Okay. Now there are two possibilities. When C3 is equal to C4, overflow or no overflow? Help me.
No overflow.
And when C3 is not equal to C4, what does it mean?
Overflow.
So can you see now the overflow bit depends on what? Help me.
C3 and C4.
C3 and C4. Now if you draw the truth table for C3 and C4, how many combinations are there? 4 combinations. 0, 0, 0, 1, 1, 0, and 1, 1. Now can you see here, in this case, are they same or different? The
Same.
green. Same. And now if we go to the black color, are they same or different?
Different.
Different. Okay. Now what will be the value of overflow? So if they are same, overflow will be 0. And if they are different, overflow will be 1. Help me. Any question?
No, sir.
Okay. Now if you look at here, which gate will be used for an overflow in between? Anyone? Which gate is this?
XOR.
This will be an XOR gate. Any question? Any question?
No question, Professor.
Okay. Now assume that this is now very important now. What is the size of the adder here? Here. Now can you see what is the size of the adder here?
4-bit.
Assume we have an n-bit adder. Assume we have an n-bit adder. So the input will be x0, x1, and blah 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 until what? X n minus 1. Then what?
y0 till yn minus 1.
Yeah. So this we have actually y0, y1, and blah 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 until yn minus 1, and then we have x0, x1, and 1 blah 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 until x what?
N minus 1.
And then we have c in, and then we have what? C out. And then we have
C out.
S0 and S1 and then blah 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 until what? Sn
Minus 1.
got it or not got it?
Got it.
Now if we have this adder, so now we have okay now in this example, since we are going to do, and now I'm generalizing the problem. I'm generalizing the problem. So we have, remember, now we have some, and we have an A. So basically what will go here in a 4-bit adder, remember, in the green color.
A will be the same.
So A will be the same, so the green color. So this is actually A n minus 1. Then what? A n minus 2 and blah 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 what? A1 and A0. Then we, if you look at here, so now this is a general adder. Generally we have B, which is the red color. So we need an exclusive OR gate. Yeah? How many exclusive OR gates we need?
N exclusive OR gates.
N exclusive OR. So we have actually, now we have this, can you see here? B n minus 1, and then we have S, and then we have another exclusive OR gate here. So we have so we have a lot of exclusive OR gates here. So this is also exclusive OR gate here, and this is also exclusive OR gate here. Okay, so now this will be B1 and this will be B0, and what will be the second input? Help me.
S.
S and S, and this S will also go where?
Cn.
And what will be my output? Help me.
C0 till Cn minus 1.
Yes, so it will go from C0 to Cn minus 1. Okay, so it will go from C0 to Cn minus 1. So this will actually go to C0. So the output will be actually, can you see here? So I will not just using. So this is actually C0, then C1, and blah 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 until Cn minus 1. And Cn, sorry, Cn minus 1. Okay. Okay. Now I will not call it as okay. Now please remember, this is my, then we have, okay, this is Cn and Cn. Then there is, okay, I will not confuse it with, sorry, there is some problem. Let's assume we want to compute. So we want to compute k. K is equal to we want to compute k. So this is actually k0, because I don't want to compute this with Cn. K0, k1 until what?
Kn minus 1.
Okay, and now we have this Cin. So now we have Cin. This Cin is C0. This will give me what? C1.
C1, C2, Cn
and
minus
then
1.
C2 and blah 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 blah. And then we have what? And please remember, in the last stage it will be Cn minus 1, and in the final Cout is actually what?
Cn.
Cn.
And what will be overflow? What will be overflow signal? Help me.
Cn XOR Cn and minus 1.
Got it or not got it?
Yes.
Got it.
Yes, this is how it works. So now Thomas asked this question that how can we design like an overflow signal? So now we can see here. So now this is, everything is here. So now here with this is a general n-bit adder. This is a general n-bit adder. Okay, this, the first input will go directly. There, how many exclusive OR gates will be there? How many exclusive OR gates will be there?
N and then 1 for the overflow.
And this operation, this is the select line. Okay, so this is a select line, and then we have Cin and you blah blah blah. So now you can see it's subtracted. It is actually a plus b plus 0, and it is a plus this will compute to a minus b. And how we got the overflow? So now if you look at the overflow, so now
Cn minus 1 XOR Cn. Yes.
yeah, got it. You can see here, this is my now the overflow. Here yours is the overflow. Any question? Clear?
Clear.
Now another $1 million question. Another $1 million question. Okay. Assume we have a signal A. Okay, no, maybe I will use some new slides. So. Okay. Assume we have some signal A. And A is equal to A3, A2, A1, and A0. What is the size of A? Help me.
4.
Just I'm taking an example. Okay. If we have, it's a 4-bit signal, and now we do with the binary numbers. We already did with the binary. What is the weight of A0? 2 to the power 0. Its weight is 2 to the power 1. Its weight is 2 to the power 2. Its weight is 2 to the power 3. Let's say if it's any numbers. Okay, this is its weight. What is the weight of A0? Help me.
1,
Then
2, 4, 8.
got it. Any question? Let's assume A is equal to 0, 0, 1, 1. What's the binary? What's the decimal value?
3.
Actually 1 plus 2, which is actually 3. Okay, now what we are going to do, if we have an A, which is actually 0, 0, 1, 1, and let's assume I put 1, 0 in the end. What is now the value number? Help me. If you convert now.
6.
Okay. Now what do I do? So now I'm putting 1, 0. So I'm putting 1, 0. Okay. Assume that I replicate, I copy and paste this A. Let's assume I'm writing it 0, 0, 1, 1, and I put 2 zeros here in the end.
12.
What will this give me?
12.
So it means that now, if we put 1, 0 in the end, it will be what? Help me. What is this 6 now?
Multiply by 2.
So this is actually 3 multiplied by 2. And what is 12 now? Help me.
3 multiply by 4.
So if we put 1, 0 in the end of any signal, so it is actually multiplied by what? Help me.
2.
2. 2 zeros.
4.
3 zeros.
8.
Any question? Any question?
No, sir.
Okay. Now, assume that we want to perform some task, and we want to design an efficient circuit. Assume we want to design an efficient circuit. Let's assume we want to design P is equal to 2A plus four B. Got it or not? Got it? And assume A and B are 4 bits. So A is 4 bit and B is also 4 bit. Okay. Now we want to compute 2A. What will be 2A now? Okay. Since A is, sorry, what will be 2A? Help me. Can you help me?
A with 2 zeros.
No. Can we write it? A3, A2, A1, and A0. How many zeros should we need to put?
1
1.
zeros.
1, 0. Okay. Now let's say we want to compute 4B. How many zero we need to put?
2.
And what will we write here?
B1, B2, B3.
And since we have B3 here and we want to compute it here, so now I need to put it 0 here. Let's assume this is an unsigned number. Okay, I will need to put it here. Now if we want to add these two, so what we get here? What is this thingy?
0.
No, what?
0 plus 0 is 0 here.
No.
Oh,
What is this
okay,
thingy?
P0, P1,
P1. What is this thing?
P2, P3, P4, P5.
Any question?
No, sir.
Got it? Okay, now what we want to design this thing, since we want to design this thing, so what we are going to do, so now what I'm going to do, I'm copying a paste as you do in your homework. And I want to design an efficient circuit this. So now what will be my P0 now? So can you see here my P0? This is my P0 is actually 0. And what will it be 1? Help me.
A0,
A0.
A0. Okay, what will be my P2 now?
A1 plus P0.
Okay, so we need a full adder or a half adder?
Half adder because we don't need
Half adder because we
Cn.
do not need, there is no carry. There is no carry out. Okay, so now we need a half adder. And what will be the first input to the half adder? Help me.
A1,
A1. The first input to the half adder will be A1. What will be the second input to the half adder?
B0,
What will be the output of this half adder?
P2,
Since this is a half adder, so it will produce a carry and it will go where? Where did it go?
Cn for the full adder.
In for the full adder. And now we have this full adder. What should be the input to this full adder?
A2, B1,
A2 and then B1. What will be my output?
P3, and C out.
And then it will produce a C out. It will go to our full adder. And then what will be the input for that full adder? Help me.
A3, B2,
A3 and then what?
B2,
B2. And what will be the output?
P4, and C out.
And then we have C out. Now we need a full adder here or a half adder here? Because for the last
Full
one,
adder.
we need. Hmm?
Full adder.
No, no, no. We need a half adder. Why? Because this is 0. So half adder has 2 inputs. Got it or not got it? Hamas.
Got it.
Okay, and what will be the output of this thing? Help me.
P5 and C out.
And this C out, you can treat this as P6. So if we are adding this 2a plus 4b, how many bits are required to represent the whole number? 1, 2, 3, 4, 5, 6, 7. 7 bits are required to represent the whole number. Any question?
No, sir.
And now I will prove it. Why 7 bit will be required? Why 7 bit will be required to represent it? I will prove it now. Okay, now we want to compute 2a. Okay, we want to compute 2a. What is the maximum number for 2a? So 2a is equal to 2 multiplied by 15. And what is 2 multiplied by 15? Because a is a 4-bit number. So if it's a 4-bit number, so the maximum number will be 15. 2 multiplied by 15 is 30. Now we want to compute 4b. What is the maximum number? Help me.
4 times 15.
15. And what will be the number?
60.
60. And think for the maximum number. If we compute these two, what will be the result now?
90.
90. And to represent 90, how many bits are required?
7.
7 bits are required. Because it lies between 64 till 128, so this 7 bits are. That's the reason we require 7 bits. Any question? Any question?
No, sir.
Okay, now. So this is how my working is there. So now can you see here? Now we have this thing. Okay, now these are other examples that I did, but I will show this with working. So now can you see here? Now this is now my task. Now this is my task one. This is an unsigned number. So you can see with 2a plus 4b. So this is 2a plus 4b. This is 2 multiplication by 8. And maybe k0 to k6. So this is k0. Then a0. We need a half adder. We do not need a full adder here because there is no carry in. Now this carry out from this half adder will go to the carry in for the next stage. And now here a2b1, the carry out from this will go to the carry in for the next stage. The full adder, and in the last we need a half adder. Got it? Any question? Yes.
No.
Any question? Should we proceed?
Yes.
Yes. Okay. Now this is how we did it. How we do this. Okay. Now I'm going to do another task. So let's assume if we want to do another task. So this is 2a plus 4b. This we did this. We did this. Okay. 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 So let's assume this is another task. Some more. Yeah, maybe. Okay, let's assume we want to perform this task. Four A plus 8B. What is 4A now? Yes. How many zeros?
A3, A2, A1, A0, 0, 0.
Any question?
No,
What is
sir.
8B? How many zero we need to put?
3.
Then what?
B0, B1, B2, B3.
Okay. And then let's assume this is my P. What is this thingy?
E0, P1, P2, P3, P4, P5, P6.
And then we get what?
P7
P7.
it says overflow.
Yeah, because to avoid overflow, we need 8 bits. How many bits we need? How many bits we need?
8.
8 bits. To avoid any loss of data. Okay. How many half adders?
2.
So we need 2 half adders. Okay, now can you see here? Now we need 2 half adders. So now we need this, and this. So these are what? Full adder or half adder?
Half adder.
And how many full adder do we need?
3.
1, 2, and 3. We need this full adder. Can you design this? Can you design this at home?
Yes.
Okay. Can you design?
Yes, sir.
So now we can also design this later on. So now if we design this, So how we can do this? So now what we are going to do? So now we have this, then we have. So what I'm going to do? So I can just copy this. Okay. So now we have P0. What is P0? 0. P1,
0.
0. Then we need half adder. So now for half adder, I'm now using a yellow color. Okay. For half adder, I'm using a yellow color. So for half adder, and then we have, then for the full adder, I use the blue color. So one full adder, other full adder, and other full adder, and for all also the half adder, I'm using the yellow color. Got it or not got it? Okay. So now what will be the output for this? Help me. P1,
A0.
P2, P3. Yes. P4. No. How many? P0, P1. This is P2. Sorry. P3, P4, P5, P6, and then the carry out is what? P7. Okay. And then
Yes.
the carry out for this will go here, 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 and here. Got it? And then we have basically now we want to connect A. So now here is A0, then A1, then A2, and then what? A3. Okay. Now, what will be the second input?
0.
No, there is one mistake
B0.
here. There is one mistake here.
Professor, for the last one, how is that a carry?
No, 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 no. Sorry, this is a mistake here. Can you now tell me where is the mistake? Where is the rubber now?
Is there no
The
need for a
last
half
half adder.
adder for P2?
Don't need an half adder here. So this is P2 is actually what?
A0.
A0. So we don't need this. And this is half adder or full adder?
Half adder.
Half
Yeah.
adder.
So we need a half adder here. Yes, you're right. So we need a half adder here. So we do not need a full adder. We need a half adder. So this is a half adder. Got it? Don't need. Got it? Any question?
Professor, for
No,
P6,
sir.
don't you need a full adder?
Hmm?
For P6, because there is a carry in, right? So we need a full adder, right?
No. For P6, because we have 0 for here. Because this is 0. When it's 0, so this is A3, and now for this one we do not need. For A0, this is A2. So this is no, sorry, this is A0. Yes, A0, then we have A1, then we have A2, then we have A3. You're right. You can read it. Please do it at home, okay? So you can do this at home. This is your homework now, because I'm not going, so this is wrong, so I'm just deleting it. Okay, so you please don't do that. So this is like some wrong working, so I'm not, please do it. Please do it at home. So for this we need full header. So we need full header for here. We need a full header here. We need a full header here. We need a full header here. We do not need a full header. And for the last one, this one, we need a half header. Got it or not got it? Any question?
Professor, in the previous
Professor,
slide.
isn't it half adder?
Yeah, for A1, B0.
Yeah. Very good. Thank you for the correction. So what I to do? So this one is also half header. So we need two half header and two full header. Any question? What I'm going to do now, I'm not